In this problem, we have given the two flat plates and the boundary layer is shown, viscosity is given, density is given, velocity is also given to us. And the distance of separation of the two plates is given, that equal to 1 cm. So we can show these two distance. So this is the boundary layer thickness for first plate and second plate, and this is the total distance of separation. So this distance of separation is 1 cm. We have delta equal to 0.5 cm. We know Reynolds number is rho v into x divided by mu. Rho is 998, velocity is 0.5 into x, mu is 1.002, 10 to the power minus 3. So this is 4.982, 10 to the power 5. And for laminar flow, this flow is laminar. We have delta equal to 5 into x upon under root of Rex. So we'll substitute delta equal to 0.5 is cm is 10 to the power minus 2 is equal to 5 into x upon under root of 4.98 times x 10 to the power 5. So from this we can obtain x. We are given a horizontal cylinder, heat flow is perpendicular to the axis of cylinder. We are given the h value and k value, k of fluid is given. We have to calculate Biot number and Nusselt number. For external flow, characteristic length is same as diameter. So we have Nusselt number equal to HLC by K. Value of h is 10. Characteristic length is 0.4, that is diameter, divided by thermal conductivity of fluid is 2. So this number is 2. Biot number is given as HLC by K, where K is of material. Characteristic length is given as V by A is equal to pi by 4 d square L divided by pi dl. So we get d by 4, that equal to 40 by 4 equal to 10 cm. So we will substitute here. Value of h is equal to 10, LC is equal to 0.1 and km equal to 2.5. So this is 0.4. Horizontal cylinder with diameter equal to d, length equal to L, thermal conductivity K is kept in a steel air, and heat transfer coefficient H and K are respectively to find out. That is Nusselt number you have to find out. So Nusselt number in case of this is given by HLC by K. Since cylinder is horizontal, so characteristic length is same as diameter. So H multiplied by D divided by K of fluid, that is Ka. So choice B is correct choice. The ratio of momentum, diffusivity, thermal diffusivity is Prandtl number. In this one we have to match the pair. Reynolds number is given by rho v d by mu. So the choice A is matched with 4. Prandtl number is given by mu Cp by K. So number 3 is matched with B. Nusselt number is given by HLC by K. So that is the choice 1 is correct. Mach number is V divided by C, that is 2 is correct. So answer B is correct choice. We are given a flow or a heated plate, hydrodynamic boundary layer thickness is given as 1 mm. We have to calculate thermal boundary layer thickness is 2 mm. So where HBl is less than TBl. So first of all we will calculate Prandtl number, because Prandtl number gives the idea about the kinematic viscosity and thermal diffusivity. So delta T by delta H equal to 1 by Pr to the power 1 by 3. Delta T by delta H equal to 2. From this we can find out Prandtl number and hence we can conclude it. In this case we are given Prandtl number equal to 6 and we want to find out the relation between them. So it is Pr to the power 1 by 3. So it is answer is 0.55. So delta T is 0.55 of delta. So delta is greater than delta T or delta T is less than delta. Choice B is correct. In this case Prandtl number is greater than 1, so we have same answer that we have just discussed. So for this quick calculation we assume Prandtl number equal to 1000, that is 10 to the power 3, and delta T by delta H equal to Pr to the power 1 by Pr to the power 1 by 3. So by substitution 1 by 10 to the power 3 and 1 by 3 is 1 by 10 is 0.1. So delta T equal to 0.1 of delta H, means delta H is greater than delta T or delta T is less than delta H. Choice A is correct. What is the Prandtl number? You have to find out. We are given the kinematic viscosity. pressure is given, the temperature is given. Prandtl number is given by mu Cp by K. We don't know the density because kinematic viscosity is given. So density is given as P by RT, that is 10 to the power 5 divided by 300 into 300. So we have 1.11. We know that mu is given by a product of rho into nu. We'll substitute this value back. So we have 1.11 into kinematic viscosity is 1.8 10 to the power minus 5. Cp is 700 and K is 0.02. 0.7. In this case, we have to find out the Reynolds number, critical Reynolds number is given, and you have to find out what is the distance LC for Reynolds number equal to 1 into 10 to the power 5. So critical length is given as 2 meter, and here we have to find out the distance x for Reynolds number equal to 1 into 10 to the power 5. So our entire flow is laminar flow, so we can use the Reynolds number equation, which is given as Reynolds number equal to V into LC by mu. This number is constant for both types, so Reynolds number is directly proportional to LC. So Re critical divided by Re equal to X critical divided by X. Substitute all value. Re critical is 5 into 10 to the power 5, Re is 1 into 10 to the power 5, X critical is equal to 2, X is equal to, we have to find out, his answer is 0.4. Castor oil at 25 degrees Celsius flows over a flat plate of 0.1. Length is given as 4.5, maintained at temperature equal to 95. You want to calculate thermal boundary layer thickness. Thickness is given to us 270.4. So straightforward problem, delta T by delta H equal to 1 upon PR to the power 1 by 3 or PR to the power minus 1 by 3. So first of all, we'll calculate delta T. So Prandtl number is not directly given, so this is 270.4 into 903 to the power minus 1 by 3, 28 mm. We are given all property and HBL is given to us. We have to calculate delta T. First of all, we'll calculate Prandtl number mu Cp by K. Mu is 25 into 10 to the power minus 6. Cp is 2000 and thermal conductivity is 0.05. So this answer is 1. For Prandtl number equal to 1, delta H will be same as delta T. Choice B is correct. The heat transfer coefficient you have to find out. The average value you have to find out. Local heat transfer is given. So use the mean value theorem. Integral of Hx dx upon integral of dx. Substitute 10 into x to the power minus 0.25 as Hx into dx upon L. L is given as 3 meter. So we have 10 x to the power minus 0.25 plus 1 is 0.75 divided by 0.75 divided by L. And upper limit is from 0 to 3. So we have 10 divided by 0.75 into 3 and 3 to the power 0.75. So your answer is 10. A coolant of fluid at 30 degrees Celsius flows over a heated flat plate maintained at constant temperature of 110. TW is given as 110. This is the wrong answer. As per the temperature distribution is given as 30 plus 160 into e to the power minus y. So if we use this distribution at y is equal to 0, we'll get the answer equal to 190. So 110 is wrong answer. This time we'll use the Fourier law and the Newton's law of cooling. We have Q equal to minus AK into dt by dy equal to H into A into TW minus T infinity. So from the temperature distribution we can find out dt by dy. So dt by dy equal to simply 160 minus y. 160 minus 1 at y equal to 0. So that answer is minus 160. So we can get H from this. Area will cancel. K into dt by dy at y equal to 0 upon TW minus T infinity. Value of K is given as 1. This is into minus 160 divided by 190 minus 30. So answer is. This time also we are given the temperature distribution and we have to find out the heat transfer coefficient. So this time TW is 60. If I put y is equal to 0, I will get TW equal to 50. And we have same equation, h equal to minus k into dt by dy at y is equal to 0 upon tw minus t infinity. So we have k equal to minus 0.65, dt by dy is 640, at y is equal to 0. We have 50 minus 60. Minus minus will cancel and we'll get positive answer 41. This time we are given the temperature distribution, and again you have to find out the heat transfer coefficient. So if we solve for T, we'll get Tw plus T infinity minus Tw into 1 minus e to the power minus 3500 y. So first of all, we have T infinity given, that equal to 400 Kelvin, K is given as 0.03 and T wall is given as 300. To calculate h, we require dt by dy at y is equal to 0. So first term derivative is 0, second term will be as it is T infinity minus Tw, that is 400 minus 300. Derivative of 1 is 0, minus minus is plus 3500 into e to the power 0 is same as 1. So you have to solve this value at y is equal to 0. 100 plus 3500. So we have h equals to minus k into dt by dy at y is equal to 0 upon Tw minus T infinity. So we have minus 0.03 into 100 into 3500 divided by Tw, 300 minus 400. Answer is 105. In an experiment, local heat transfer coefficient we have to given in the form of NUX 0.035, Reynolds to the power 0.8, Prandtl to the power 1 by 3. We have to calculate Hx in terms of HL. So NUX equal to Hx into x by k equal to 0.035 u infinity into x by nu 0.8 into mu Cp by k to the power 1 by 3. We will solve for Hx first. 0.035 into u infinity divided by nu to the power 0.8. X will write down later on, mu Cp by k to the power 1 by 3. We have x to the power on the left hand side and right hand side, we are left with minus 0.2. Let's say this constant is a. So we have Hx equal to at L is equal to a into L to the power minus 0.2. To calculate average, we'll use the mean value theorem, that is integral Hx dx upon integral dx equals to integral a into x to the power minus 0.2 into dx upon integral dx, and limit is from 0 to L. So integral of numerator is a upon L, x to the power minus 0.8 is x to the power 0.8 upon 0.8. So is 1.25 into a into L to the power minus 0.2. Now a into L to the power 0.52 is same as Hx. This number is same as Hx. So average value is 1.25. So h bar upon Hx is equals to 1.25. The temperature profile is given to us and delta Tx is given to us. We have to develop the correlation for this. So we have Hx equal to minus k into dt by dy at y is equal to 0 upon Tw minus T infinity. So we have T is equal to Tw plus T infinity minus Tw into bracket 3 by 2 y by delta T minus 1 by 2 y by delta T cube. So we have to first find out dt by dy. So dt by dy equals to first term derivative is 0 plus this value is same as T infinity minus Tw. From this term 3 by 2 delta T is common. Derivative of y is same as 1 minus 1 by 2 delta T cube Derivative of y cube is 3y square. You have to solve this value at y equal to 0. So second term will be equal to 0. So we left with T infinity minus TW into 3 by 2 delta T. So we'll put this value back, and we are already given the value of delta T. So we'll just put up that value and we'll solve it. So we have Hx equals to minus K into 3 by 2 times delta T into T infinity minus TW divided by TW minus T infinity. So that term is get cancelled, minus will become plus. So we left with K into 3 by 2 delta T. So we have Hx equal to 1.5 times K upon, now we'll replace delta T as 4.53 into x, and rest term we'll write in the numerator, Re to the power 1 by 2, Prandtl to the power 1 by 3. So we will get that number 1.5 divided by 4.53 is 0.332. Hence we prove the relation. So we have Hx into x by k, that is Nusselt number actually. Relation already proved is 0.332 into Reynolds to the power 1 by 2, Prandtl to the power 1 by 3. This is called as local Nusselt number.